Good. So we're going to look at one of the most contentious areas in society just now, and that's around key exchange, and especially around the usage of end-to-end encryption and how we set these things up. So the areas we'll look at is the diffie-hellman method. So it's been around for over 40 years, and it's still going strong. And it's the basis of many of the methods that we'll look at. Then we'll look at some of the weaknesses of it. It's caused a lot of problems, poodle, freak, and so on. So many of the major security problems that have happened through the usage of the diffie-hellman method. Then we'll look at how elliptic curve diffie-hellman works. So just now, when you connect to the Wi-Fi network, it's elliptic curve diffie-hellman. If you're buying bitcoins on, if you're using the Tor network and so on, it's elliptic curve diffie-hellman. So we'll find that that's the most preferred method when it comes to IoT and in building new infrastructures. And finally, we'll look at how we can pass how we can pass a key using public key encryption. But I highlight that TLS 1.3 has dumped that method, and we'll see why that's the case. So if possible, always upgrade to TLS 1.3 from TLS 1.2 if possible. Then finally, we'll look at what are called key distribution centers, and it should be relevant to your coursework. So when I outline the coursework, I want you to build your own secure infrastructure using key distributions. Oops, just let me get that back to the start. Okay, so that's been our roadmap up to now. And what we're going to concentrate on is the key exchange part. So we need some way to make sure that we can create a tunnel between Bob and Alice so that Eve, if she's listening, can't act as a man in the middle, can't modify things, can't change things, and so on. So our ultimate goal is to make sure that that connection is secure and stays secure forever and ever. So it doesn't do any good for us to secure the connection now, and in 1 year Eve detects the keys and discovers all our communications. So we need to look at how we can pass the key between Bob and Alice. And just now, we're going through a period of what would be called crypto wars. So there's a challenge between the rights of people to privacy and secrecy against the rights of society to protect itself against those who might do it harm. And obviously for centuries, governments, agencies have been able to listen to secret communications through the postal service and so on. And only now do we have a technology which can actually stop anyone from listening to secret communications. And for 99%, for a vast majority of the communications, there is nothing malicious and bad going on. Unfortunately, there are people who use end-to-end encryption to do bad things. So we need to understand the challenges that we face and understand the methods that we use and define really the ways that we could possibly get around some of these issues. But we're technical people, and we're meant to be designing systems that are secure and robust and so on. So we must understand that there are political pressures in everything that we do, and there are also ethical issues that you should always consider in everything that you do. So what we have, as we've seen, is that we use our keys to be able to prove identity, use a public key to sign for things, and we use a key exchange to be able to generate a key. But unfortunately, some governments of the world are scared by the usage of end-to-end encryption. So in Australia, it was quoted that the laws of mathematics are good, but the laws of the land of Australia should overrule those mathematical laws that we look at. And you can see how contentious this becomes. So there is no magic wand there that will take the elliptic curve, diffie-hellman, and then the good guys will wave a wand and be able to decrypt, and the bad people won't. There isn't anything in there that allows you to break the crypto that we create to allow it to be used for good purposes, but not for bad purposes. So it's either one way or the other. We create the math so that it does secure, or we break it. So that's the tension that we have. And we see even in the UK there is this tension around the usage of end-to-end encryption. So can I ask you, who uses WhatsApp here? Yeah, about half. Who uses Telegram? The other half. Any other ones that you would use? Signal. Viber. Instagram. It doesn't work just now. there's no encryption.
What about iMessage?
What was it?
iMessage. It's not stored in the cloud.
Yeah, that works. So Facebook bought WhatsApp. It was interesting. And then just before that happened, WhatsApp put in end-to-end encryption, which kind of killed off a good deal of the business model of Facebook, which is all based around understanding what people like and who their contacts are, and so on. So there's been a bit of movement in terms of that Facebook integration with WhatsApp. So it looks like they're moving towards recording the metadata of conversations at either end. So you're still using end-to-end encryption, but the bit that happens at the start and the end could be mined. But there's also what's the other move that's happening just now with Facebook? And they need to watch how they tread with this one.
We're combining Facebook and Instagram and WhatsApp.
Yeah. So they're bringing the three platforms together, which means that each of the IDs of the users on those platforms can then message. What they're being watched for very carefully is what they then do. If they break the end-to-end encryption in some way, they're going to be in trouble from the technical community. But I think it's likely not to end up that way, because they would have such a backlash against that. So in the UK we see that sort of tension, and unfortunately you see headlines like this where a UK government, and it just shows that governments and politicians often don't understand the technology that happens underneath. So this was a UK government official getting mixed up between hashing and hashtags. Hopefully by this week in the module you should know the difference, okay? I'd worry if you didn't, if you got mixed up between a hashtag, like a P tag, and hashing. So really I think politicians and governments sometimes think that there is a magical thing that will allow them to be able to break this crypto that we've created without compromising the system. And then in the end, politicians often end up saying, well, We don't actually know the technology, but we know it's bad. But on the other hand, it's good because it protects the rights of the individuals. And it doesn't end up with politicians that do this badly. So Equifax were hacked for at least 6 months or so, by which time executives were selling their shares. They were breached because they didn't patch they didn't patch their infrastructure. It was 10 out of 10 for a security risk, and they didn't patch it, and they lost a whole lot of data. And then the CEO was asked, well, did you encrypt the data? And he replied, I have no idea. So please make sure that your CEO understands how to encrypt data and ask the right questions. A CEO should not stand up in front of an instant response query and say they have no idea whether citizen data has been encrypted or not. It's their responsibility to look after their customers' data. So increasingly we need to understand the usage of encryption and so on. And then it happened with the TalkTalk hack that Dido Harding went on Sky News and told the world that she didn't actually know if the data was encrypted or not. So it's important that you understand how to.
So when you talk to your customers, apart from obviously doing interviews like this, but you're going to be communicating with your customers, sending emails and so on.
It's a bit difficult to hear it from there, but this was Dido live on Sky News, and it was a car crash of an interview. She says it's okay. You'll receive emails from us, and it'll have a link that looks as if it's TalkTalk in the body. You can trust that, and and many people were saying, listening to this, was saying that is the wrong advice, and the scammers were just getting ready to send all these fake emails. So it's very important that you understand how to respond to an incident and to clearly articulate it. And then the UK brought in this bill, which involved the mass harvesting of data that might be used at some time in the future. And it's caused a lot of problems for the UK in that they will have difficulty implementing a GDPR solution, having the Investigatory Powers Act there, which is basically mass harvesting. So governments around the world are really struggling with this technology. So what we need to do is to set up a tunnel, and we create a shared key, and that's it. So for end-to-end encryption, only Bob and Alice will have that key. On your companies, you'll probably find, if you work for a bank or a company that is highly secure, you'll find there's smart firewalls in the way, and those smart firewalls can proxy keys, and it can look as if you're connecting directly to Gmail, but actually there's an intermediate device in between which is proxying the keys. But in a pure end-to-end encryption solution, only Bob and Alice will have that key for that session, and it will be unique across the whole of the internet. So we get the concept of the Snowden phone, and the Snowden phone would be something that would implement end-to-end encryption. So this paper here, and I'll send you the link to it, identifies the end-to-end applications which could be used. So they evaluated Signal, WhatsApp, Wise, Viber, Riot, and Telegram. And you can actually see that none of them are actually perfect. So you might think that Telegram is good, it's open source, it's not owned by anyone, and it would be perfection. But you can see that there's a few points that it struggles with. So the solutions aren't quite there, and for your business you need to understand what are the features that you need for your secure communications and what would be the best one. But with WhatsApp being owned by Facebook, then you can't be sure that there's a guarantee that the source code won't be modified at some time in the future. So the Open Whisper systems, and we see here Bruce Nair talking about this, becomes important that we understand the scope of what it is we're trying to implement. So with key exchange, what we really want to do is to be able to generate a key so that both Bob and Alice have that unique key for the time of the connection. And then for Eve not to be able to listen to their communications. And the solution to this problem was found by Whitfield Diffie, and himself and Martin Hellman wrote an amazing paper which really changed the world of security. So this was even before public key encryption with RSA. They published this method, and it's still active to the day. The other issue that we have with key exchange is defined by two problems. One is forward secrecy, to make sure that a hack in the future will not compromise any of the previous sessions that we've had. And it's also got to be what's called ephemeral. And ephemeral is that we don't want to be generating the same key ever again. We're using the same parameters, and we need to make sure that every key that we create is unique and cannot be linked to any previous ones from the past. So the solution really was developed by something that's based on logarithms. And logarithms says that a to the power of x times a to the power of y is equal to a to the power of x plus y. And a to the power of x to the power of y is a to the power of xy. Hopefully you've all seen this at school. You probably hated logarithms at school, but my goodness, they are solving a fundamental problem. Okay, so that's the core of what we do, is based around those two methods. So Bob creates a random value x. The length, the number of bits that value has, defines the security. If I can search very quickly all the values of x, I'm going to be able to break this. So we pick a big enough value to make sure that Eve can't go through all the possible values that Bob has generated. Then Eve does the same thing. She generates a random number, and we'll call it y. Then we agree on a shared number. 2, 3 are typical generators. Quite low numbers, you might think, but we're going to end up with very large numbers. So Bob raises a to the power of x and sends that over to Alice. And Alice does the same thing with her number and sends it back. So Bob now has a to the power of x, y, and Alice has a to the power of x. Because of the difficulty with discrete logarithms, it's impossible with the computing power that we have to find out what the values of x and y are. That's the fundamental challenge within discrete logs, is that you cannot find that value for a reasonable cost. So those values go over. So there's one little thing I'm not adding here. You take the mod of a prime number. It's called a finite field So if you did a mod of the prime number that they both agree with, then that's the only modification that we have there. So then we pass over the numbers, and Bob takes his value and raises it to the power of x, because he knows x, and Alice takes the value she got from Bob and raises it to the power of y, both still mod p. So what can you now tell me about the values that Bob and Alice have?
They're the same.
Same. Why are they the same? What is it?
A is to power y multiplied x, a is to power x multiplied y, same.
Yeah, so it's a to the power of x, y, mod p. And mod p is good because it yeah.
It was going to be that. Why do you need to do modular arithmetic?
So you need to do modular arithmetic because the numbers are going to be ginormous. They're big enough anyway, but my goodness, they'll be absolutely massive. So we defined what's called a finite field, and it basically constrains it between 0 and a prime minus 1. And we can still do all the maths. So add, take away, divide, multiply, all still work, only because we use the mod of a prime. If we don't use the mod of a prime, it all falls apart. It doesn't work.
Then how is the prime share the prime number?
That's right, yeah. So both Bob and Alice agree to the prime. Eve knows A, and Eve knows the prime. So Eve must now very quickly go through all the values of x and y until she finds something that would match to what Bob sent and what Alice sent. So she needs to find out x and y. Okay, so she would compute to find that a to the power of x. She would find that. She would then compute Alice's value until she found the value of y that would work. That she can see the communication go back and forward. So if she has enough computing power, she'll work at x and y. She just takes a to the power of x, y, mod p, and she has the key. So she has now cracked the tunnel. Unfortunately, as we'll see later, that this really happens, that many websites were open to this because of sloppy admin and setting up these values. She could pre-compute. So if we are using the same G and prime number, she'll just get a big computer to try and pre-compute as much as she can, and then she might be lucky and picking off a value of x and y that she's already pre-computed, and she just has a lookup table and can actually crack the tunnel. And it did happen, and it caused a lot of problems. Okay, so there's how it works. We take our g value, we raise it to the power of x, we take our mod n, we send it over, we take the value we receive and raise it to the value that we have. Remember, in Python, it's double star, and the mod is what?
P minus 1.
No, what's the mod operator?
Percent.
Percent, yeah. So that's our percent. That's the only two things we need. You can do it in a couple of lines of Python, and it should all work out. Okay, so there's an example there. So what I'll do is I'll just show you quickly. Hopefully I can get this to work. Okay, so I'll get my Python. So just so that I've not set this up, so somebody give me Alice's value number, just any number. Your favourite number? Anything? It's not an exam question. 7. Okay. And Bob? 77, did you say? 67. Oh, that's the only one that will not work with, but we'll try it anyway. Okay, what's your favourite prime number? Make it kind of high. And give me a prime number, please. Because it'll not work if you don't. Give me a prime number.
89.
What?
89.
That is a prime number, is it? It sounds like it. I always worry when there's a 9 at the end. I always worry if there's a there's an even number at the end, apart from one case. What's that one case? There's this joke. What's that? 2, yeah. There's this joke, and it's a really sad joke, is that the shortest book in the world is the even prime numbers, and it's on page 1 it says 2, end. It's such a sad joke. I'll cut that bit out to the presentation. So we'll go for a prime number of 89. Hopefully it is a prime number. I'm just trying to think exactly. Sorry, your screen isn't showing there like that. Okay, so Bob's value will be, and we'll pick a G value. Let's go for 3. Hopefully that's going to be okay. It's a typical value that we would use. So Bob's value will be G to the power of B percent and P. Okay, so we'll just see what that looks like. Okay, 76, and then we'll get Alice's value, which will be, that's Alice. If I could get my cap lock to stop. So Alice's value that she's going to send will be that, and we'll have a look to see what she's got. Okay, so it's 51. So Bob sends over his value and Alice will send over her value. So the key should be equal to Alice's value to what? To tell me the variable name.
B.
To
Right, B.
To B.
Yeah, what Bob did for his key.
Yeah. To B,
Then mod P.
then mod P.
Wait, let's be P minus 1 or P?
That's P. Okay, 43. Right. It's going to be a disaster. I just know it is. Okay, and then Bob's value will be raised to A. Bob's value. Okay, please work. And it worked. Yeah. I probably went right over your head. You can watch it back later. But I did get that to work, I can assure you. And I didn't prime you at all for any of the numbers. That bad pun anyway. So that's isn't that amazing? I think that when I discovered that, I thought, wow, that's just fantastic. The simplicity of it, the beauty of it. I just couldn't believe that did that, and that's the thing that law enforcement agencies, that little exponential thing, that's the thing that really they struggle with greatly. Obviously, the numbers that we're dealing with are more like so for a 1024-bit prime number. Well, we'll go for 512. So if I have if I have a 512-bit prime number, it looks a bit like that. Okay, it's a big. That isn't a prime number, by the way, of course, because it's even. But that's the numbers that we're dealing with. Okay, so you're not dealing with the little dinky little numbers, and it doesn't take long for us to get very large numbers. So if I just take a value like that, my computer's just crashed, I think. so hopefully it isn't. It's not going to take a long time to do that. So the calculation of 2 to the power of a big number is a big number. Does anybody know? So if I did this in pure Python, it's rubbish. It won't compute. Does anybody know the little magical little operator that you use in Python, the little method? So there's a method called math.pow, and then it's g to the power of a mod p. And it has some special little method in it that doesn't do that a to the power of b, because it would just take too long. It does a special thing that's very quick. Have a look at the difference between the two methods, and you'll find one will eat up all your CPU and take hours, and the other one will do it very, very, very quickly. So that's the kind of core of that method there. Unfortunately, it doesn't always work, and you've got to pick a value of g, which means that when you do your calculation, for every value of x, you get something unique on the other end. And it's all to do with the prime that you use. So I've done some very simple ones there. So 2 works because each of the values that are coming out are between 0 and 10 up to the prime number. Does 3 work? No. 3 doesn't work. For a prime number of 11, 3 doesn't work and can't be used as a generator value. Does 4 work? Does 4 work? Can I pick g is equal to 4 if I use a prime number of x? Does that work?
No.
No, because it's not giving us all the possible values. Does 5 work? No. Does 6 work? Yes, 6 works. So there's in the lab today you'll investigate that. So it's not always that it will work and it will create the value that we actually need. So how do we create the parameters that we need for our diffie-hellman exchange? Well, we can use OpenSSL, and if you're setting up a server or so on, this is what you would have to go through to generate your initial values of your diffie-hellman method. So we've created there our output values. And you can see here the prime number is defined here as 768 bits. And that's group 1. That's the minimum level of diffie-hellman parameters, is to use a 768-bit prime number. But don't do that. That's at the cusp of being cracked by law enforcement agencies. The generator value, can anybody see what the G value is? 2. That's it. We're just using a value of 2. So it's 2, and the prime number is there, and that's it. That's all you need for your diffie-hellman key exchange to happen, is at those 2 values. And when you create your VPN, your IPsec, actually it's these values that are already embedded into it. The biggest problem, so group 2 is really where you should be with 1000-bit prime numbers, and if you can, go for group 5. And we can even go up higher if you want, but group 5 is for highly secure networks. The biggest problem with this is a downgrade attack. So you might think you're working on 1500-bit diffie-hellman parameters, but somebody pulls down the whole crypto of your site to the lowest security and then can crack your keys. So we'll find out when we look at tunnels that what we've got to make sure is that we kick off the low-lying fruit, and we'll see how we do that, but we would not allow a tunnel to happen if we negotiated with group 1. And if somebody wanted to connect with group 1, we'd say you're not connecting to our corporate network by using such low security. Upgrade until you get to group 2. So those are the basic parameters that we have that will allow us to create our tunnels. And it happened in 2015 with a paper called The Imperfect Security, How Diffie-hellman Fails in Practice. And they showed that everyone was using, or many people were using the defaults, the default prime numbers and the default G value. So the administrators were so lazy that they couldn't be bothered running one OpenSSL command to generate their own keys. Basically, they set up their Apache web server and they just took the default in there. And this was a typical one. And these researchers found that 7% of all the websites in the world were using just a few different default parameters. And you go, seriously? They don't have enough time to create a new prime number for their VPN tunnels. And so all that needs to happen now is that an agency will go through with that prime number all the possible values for Bob and Alice with that G value and build up a great big table. And then when they see the negotiation, they can pick off the values that are used. So it was a major problem at the time, and it was 7% of the top 1 million websites were using these default parameters. And where they were, it was hard-coded. The biggest problem, though, with the diffie-hellman method is the Eve in the middle. There is no way of knowing that Eve is in between. And the way it works is that Bob negotiates a key with Eve, and also another key with Alice. As far as each of them is concerned, they've generated a key and they're talking to each other. But basically, between Bob and Alice, we use one key. Between Bob and Eve will then decrypt and then re-encrypt again. So she's a proxy in between, but she knows the keys on the other side, and then she re-encrypts for Alice. And now, hopefully, we need to build then methods that will properly authenticate Alice to Bob within the key exchange. And we typically do that with digital certificates, as we'll see, in that Alice shows that she is Alice, and the negotiation is done directly between the two entities. The method that's most often used now is ECDH, and it's wiping the floor with every other method. Unfortunately, when quantum computers come along, quantum computers will wipe the floor with this method. So the time span for quantum computers is about 10 to 15 years. So if you're negotiating keys now, and that data still has to be secure in 15 years' time, then you need to move over to a quantum robust key exchange method. So Google has it in Chrome Canary as a test. You can use quantum robust key exchange. I won't go into the methods here, but you can use new methods that are quantum robust. But I say now that quantum computers don't find this a hard problem. So what we have is our G point on the curve. We plot a gradient, a random number, and then we get a point which is our public key. And we can distribute our public key and our G point. So this is what it looks like. There's our G value, there's our public key, and there's our private key. So this is what protects your bitcoins, really, just that private key. And the difficulty is that even though Eve has that, she can't find your private key. So that's what it looks like, as we've seen. That's what your keys look like, the parameters that are involved. There's a prime number that we're using. Again, we use mod P all the time. There's a generator value. and the A and the B value gives you the basic elliptic curve that we're actually using. This one you'll see in many places. It's a standard elliptic curve. Some people try to promote other elliptic curves, and these are seen to be insecure. But at this present time, for Bitcoin and for Ethereum and so on, this is the curve that everyone trusts and knows is correct. So it just works the same, as if by magic. This time we're not doing to the power of, we're doing multiply. And when I saw this, I thought, oh my goodness, that is just wonderful. The simplicity of it is absolutely amazing. So this time we take our G value, Alice generates a random number and multiplies that point with her random number, and she gets her public key value. Bob does the same. He generates a random value, takes the G value that they both agreed on, as we saw before, if we use that Bitcoin curve, and he comes up with a point that's above there. Okay, they then pass each other the points. I say now that Bluetooth mucked up. There was a Bluetooth bug around this, and they didn't pass the Y value of the point, and it meant that the key exchange could be cracked. So it's an X and a Y point that they go back and forward, and then Alice just multiplies the point that she gets with her value, and Bob takes his value, takes the point and multiplies, and they will both end up with the same shared value. If they want, they could take the X point of the values, and that would be their key, or they could do something together about the X and Y, but that's the core of the key exchange. And it's that method which is you're now connecting to the Wi-Fi network, and it's that method that you're actually using. And the great thing is that your mobile device or your IoT device or your sensor that doesn't have a battery can compute this quite happily, and we don't have to be messed up with the RSA type method. So we see it within the Tor network. So if we were to rebuild the internet again, it would probably be as Tor. So we built the internet, and it was basically insecure, because security wasn't a problem when it was created. DARPA, they had private networks. It wasn't really a problem. All the original RFCs were written. Security wasn't really mentioned at all. And then we had a sticking plaster. We put in SSL and HTTPS and all these things. It just isn't secure. If we were to do it again, it would look like this. So I've shown each of the keys that's used, and we're using top dollar 256-bit AES for each of those coloured keys. So we're using symmetric key encryption all the time. We take our data and we encrypt with the red key. We then encrypt with the green key, and we encrypt with the purple key. So it wraps around like an onion. And then elliptic curve diffie-hellman is used to negotiate between Bob and each of the nodes who want to be part of the network. So it doesn't have to be routers and so on, it can be people's machines. Each will negotiate a key with elliptic curve, diffie-hellman, and they will create a 256-bit AES key. Only they and Bob will know that key. As we go through the nodes, each node decrypts with its key, and we end up with the data. So on a Tor network, our data actually is revealed and encrypted at the end. How will we overcome that? So the problem that we have here is that if someone's sitting here, they can actually see what's been said. It's the last mile, it's the last bit, and the first bit. That's where an investigator will sit. To sit in a Tor network, does anybody know how to crack the Tor network? How researchers have managed. Ethically, it's horrendous. For researchers to sit on the Tor network and to break traffic is ethically bad. So don't do it. There has been a few occasions of papers being pulled for conferences of people presenting it. How do you think you would crack the Tor network?
Actually set up an exit gateway
Yeah,
for the Tor network, which you are.
that would be one way, but Tor's going to detect that very quickly because it polices its exit and its entry nodes. That is a very good.
Or malware on your machine.
Yeah.
Your machine at the enterprise.
That's right. Yeah. So that's one way, but that Tor police the networks very well. How else do you think?
Packet sizes.
Packet sizes, it could be, yeah. So that works in the lab. With packet sizes, I can tell you're watching BBC traffic, BBC News because of the burst of the traffic. But Tor network, the packets are all the same size, so it just looks a bit strange. It works in the lab, kinda, for that traffic profile. But once you add your Spotify and streaming TV and all the other apps that are running in a home environment, it just doesn't work in real life. But how would you actually crack the data? Do you think? It's a difficult question. I appreciate it.
I mean, obtain them out of the memory of the person.
Yeah, that would be the end, but the Tor doesn't cover that very last little bit.
You need to, in fact, you need to get access to the memory of
You
the
would,
person
yeah,
to use it.
yeah. And that isn't as difficult as you might think it is. So there are methods that you can examine the memory as it's running. So that is always going to be a problem. But the way that we'll typically do it is they'll sit on the network for as long as possible, and then they put a lot of nodes in, and eventually you'll win. Eventually, your whole network, all of the malicious nodes, the spies, create a connection. Oh yes. So if there's 1 million nodes, you might place your own network in there of 1,000. So you can do the maths, I don't know how it comes out, but eventually you'll win, and all of your nodes provides the whole of the chain. So that was the method that they used most recently, but Tor are watching anybody to make sure that they aren't getting these malicious nodes. And you have to create the whole of the chain to be able to do that. Or perhaps the last little bit, that's possible. So this is the way that Tor works. If you're interested, it uses this curve here, curve 25519, and does that key exchange thing with the diffie-hellman type thing, but this time it's doing it with elliptic curve, and my goodness, is it efficient in its operation. So the other method that we talked about, and which is in TLS 1.3, and we need to get rid of as quick as possible, is this method. So with this method, Google passes me their public key. I then create a session key, I encrypt with Google's public key, and I send it back. And Google will decrypt to find the session key with which key? Google's public private key, my public private key. What key will Google use? Their private key, yeah. So that works. So why is that being kicked off TLS 1.3? Why should you not use that method?
Because then every session that you've ever had with Google, if someone gets that private key,
Yeah.
they can crack all
Yeah.
these sessions.
Yeah. So a long-term hack of your private key, such as an insider leaking that key to the world, will open up every single conversation that you've ever had with Google. TLS 1.3 is gone. And we use elliptic curve, diffie-hellman, WP 3 is gone too. So the way of wrapping your public key wrapping the session key with the public key, his history. So one last little bit is what's called a key distribution center. So a large company, or even a not so large company, like a bank, will have hundreds of thousands of public and private key pairs. So how does a bank manage to keep a track of all the keys and make sure they're all secure, and to rotate them and update them when somebody leaves and the sysadmin, you're going to have to replace all your keys, and how does that happen? So many companies are moving to what are called trust infrastructures, call it fog computing. So the devices you have just now on a network is large. In an IoT world, it's ginormous. So how are you going to control all of your edge devices, all of the sensors in your networks, your mobile phones, and so on? And that can only really be done by setting up a trust infrastructure which generates keys for you. And basically, it's a bit like having a safe deposit box. So you register your key with your trust server, and they will keep your key secure for you. When you want to then create a connection with Bob, Bob has also created his safe deposit box, and you can then create a new key which is sealed that you should be using only to connect to Bob. So can you tell me the advantages of this type of system? So Trent will create the key for you, and then we'll send that to Bob and Alice. Can you tell me the advantages of that system? So we're not doing end-to-end encryption anymore, so that's not so good. But what's the advantages of using a trust infrastructure where we generate the keys?
Validation that those keys are
Yep.
the ones for each
It's validation, yeah, we can quickly, we don't have to have a revocation service that runs on the internet. We can revoke our own keys. What was that? Someone else said something? We can log all the keys. We can put them in a little, if somebody does want to have a look, then we could actually have a whole list of the keys in escrow, and we say, right, for that connection there, that was the key that was used, so let's actually have a look. And that happens in a lot of corporate environments. You might not think that, but in many systems there is a Wireshark capture of a session, and then there's a recording of the key that was used, so that sometime in the future an investigator can go back in and replay the whole of the connection. Because if you don't do that, you've lost all the detail of the packets that were sent. So that's the advantage, and tell me the disadvantage. Or is there a disadvantage of using a trust infrastructure to generate the keys? What's the downside of this?
If there's an issue and everything's affected.
Yeah, so there's a big problem if this goes down. You are relying on this for your whole infrastructure, and it's a single point of failure. So you would obviously have secondary and other infrastructures, and they would have to replicate each other to keep up to date. So although you're centralizing, actually it makes the key management, especially if you're running in the cloud. So if you're using an Azure or AWS infrastructure for all your data, then how are you going to generate your keys to be able to access your public cloud? The way you would do it is to maybe run an on-premise trust infrastructure, and it would generate the keys that would be required to be able to link to this You'd also run your Active Directory to give you the rights for the keys and so on. And that's the way that our architecture is generally going. Okay, so this is basically what happens here. So Alice registers her long-term key, and Bob registers his long-term key with the KDC, the Key Distribution Centre. Then when Alice wants to speak to Bob, she passes her ID, maybe her email address, and Bob's email address, and then the KDC looks up the keys. The KDC then creates a session key, which is random. You might log that, and then encrypts with Alice's long-term key. Sends that back. Then, for Bob, he tells Bob that there's a connection coming in from Alice that's coming up, and here's the key. So he takes the session key and encrypts with Bob's key, and all that needs to happen on the other end is that he decrypts to find the session key, and then she decrypts with her key, and we now have a key which can be used for the connection. So this is the way that we can actually create our keys. So if you're interested, that's the Python code. I appreciate I'm using ECB, which we wouldn't use ever, but it's just a quick implementation. But that's the code there that we would use to be able to find out our long-term key and then create the session key from there. So just to make sure that it works, and you'll do it in the lab today, hopefully. There's the keys there. There's the long-term keys, and these are the encrypted messages that are sent to Bob and Alice. And then when they decrypt, they will hopefully end up with the same session key at the end. We can enhance it if we want. It's a bit better infrastructure there for our keys to make sure it all works. So in this case, we don't have, Bob doesn't have to get the key, but there is a way that Alice can wrap, they can get the reply back, which wraps his long-term key into the message that's sent, and he automatically can decrypt it and discover it. So in that way, we can reduce the overhead of having to give Bob the key. Okay, so that's covered our key exchange. What we'll do is we'll have a break, and then we'll have a little challenge. Hopefully you've remembered something from the session, and we'll do, hopefully you have remembered a little bit from it. I know that it will take a little bit of study and so on, but hopefully you'll get there. Okay, so we'll have a break for about five minutes or so.